Okay, hello class. Okay, today we gonna proceed our new chapter. Okay, we recap our previous chapter. We have learned about the basic concept of the thermodynamic, which cover under the introduction of chemical engineering thermodynamic. I hope that you still remember and will understand about the basic concepts such as related to the first and second law of thermodynamic, related to the different type of the thermodynamic properties such as intensive and also extensive property. You already able to define or the different, to differentiate the difference between the open and closed system, and also the different type of the process in the thermodynamics, such as what is the isothermal, adiabatic, what is the concept of isochoric, isobaric, and etc. Okay, for this topic in this chapter, we're gonna learn about the new chapter, which is the volumetric properties of pure fluid. Okay, let me share the screen. Okay, these are the list of the learning outcome for this chapter. First, you're gonna learn about the pure substance, which you should able to define the pure substance. And then we gonna move to the PVT behavior. And for this topic, you should able to discuss the physics of phase change processes, and able to illustrate the PV, TV, and PT property diagram, and also to discuss the PVT surfaces for pure substance. Normally, we gonna cover on the water substance, and we gonna move to the equations of state, which for this equation of state, it categorized into virial, cubic equation, and generalized equation of state. Okay, by this we introduce the compressibility factor, which is Z, and molar volume, which account for the deviation between the real gases and ideal gas behavior. And last, you're gonna learn about the application of this equation in industry, what kind of the condition and the operation process for this to ensure that you can choose which equation of state for that respective application or the industry. Okay, for the introduction, let's we go through to the topic. Okay, volumetric properties defined by the space occupied by 1 mole of material at a given temperature and pressure is known as the molar volume of that material, which denotes by V. The thermodynamic properties calculated the heat and work requires of the industrial process, which these properties can be evaluated from volumetric data. And then the PVT relation, which is covered in our second topic, is important because it states the flow regime, parameters for handling the reservoir fluids, and also the pipe size. Okay, as a chemical engineer, one of the main task is to able to design the process. So basically, the PVT relation will help us to design, to conduct the design of the process. Example, to design the piping size, to design the vessel based on the behavior of the substance. Okay, what is the pure substance? Okay, the pure substance is a substance that fits chemical composition throughout. Okay, example, if in one vessel we have the nitrogen, it contains nitrogen inside the vessel. So we can classify it as a pure substance because we know the composition or chemical composition inside this vessel. How about if that vessel is replaced by air? If the vessel is solely having air inside it, so we also know the composition of air, right? Because for the air, the nitrogen and also the composition of oxygen is fixed, right? So we can categorize it or classify it as a pure substance. Okay, how about if we have a vessel that contain water, but we heat up that vessel? So basically that water can be either in liquid or vapor depending on the temperature or operating conditions supplied into it. So basically if we have two phase here, we do not know what is the composition of the water inside that vessel. So basically it cannot be called as or categorized under pure substance because the chemical or the composition for vapor and liquid is not fixed at all. Example, if we have liquid at certain composition, so the remain composition is in vapor phase, right? How about for the air? If we have air, same as water, if we heat up or given a certain operating condition for that vessel, so basically the air also cannot be called as a pure substance. So compare than the first example I give to you. Okay, for this example, the air is not a pure substance because the composition is not fixed at all. Once we introduce heat, or maybe we increase the pressure in the system or in the vessel. Okay, the PVT behavior of pure substance, we already identify what is we already define what is the pure substance. Okay, let's move to the PVT behavior. Okay, the behavior of pure substance can be described by using the PVT diagram. Okay, example, we have PT diagram. Okay, the first region here is the solid. Okay, example, we have ice. Okay, we have ice here. Maybe you can imagine that in one vessel we have ice. And then if I heat up from the ice, condition of ice is about 10 degrees Celsius. And then when I heat up or supply heat into the system, the ice started to melting and it turns to the liquid, right? From solid, it turns to be liquid when we increase the temperature at certain point. And then after that, from the liquid, maybe we heat up until 30 degrees Celsius. And then if we continue heat up this vessel, that liquid, all the ice, it will be turned to the liquid phase. There is no more solid or there is no more ice in that vessel. And then if we increase more, maybe up to 90 degrees Celsius, it will start to vaporize. Until, example, if we increase the temperature up to 120 degrees Celsius, all the liquid region or the water in a liquid region will turn to the gas or vapor, right? And if we increase more, okay, example, until it reach the critical temperature, example for water, 380 something, I think, the critical temperature for water. And if the temperature exceed that critical temperature, the vapor cannot be, or vapor liquid phase cannot be longer to turn back to the liquid. So it will remain to be in vapor phase. So basically, the point C here is a critical point which coordinates PC and TC are the highest temperature and pressure at which a pure substance is observed to exist in vapor liquid region. Okay, this is the vapor liquid region. So we have we have this vapor liquid region. But if it exists, then this point, that means it cannot be turned back to this region. So the three lines here meet at triple point when three phases vapor, we have vapor, liquid, and solid coexist in equilibrium. Okay, these are the example that I already mentioned about water phase diagram. We have the triple point here, and then for this, we have the critical point. Okay, for the PV diagram here, okay, it's the same. We have P versus V, and we have the temperature for this line. Okay, you can see here, we have the solid phase, and then we have the liquid region, and under the dome here is the two phase. We have liquid vapor region, and we have this C here is the critical point. If we increase the temperature, okay, this line, okay, let me change the color. Okay, this is the line for the temperature. So you can see here, as increasing this line, that's mean the temperature will be increased. Okay, the triple point here becomes a horizontal line. Okay, this is your triple point. You can see the horizontal line here where three phases coexist at a single temperature and pressure. So we have the single pressure and also the temperature. Okay, you can see from the figure B here, lines T1 and T2 are subcritical temperature. That's mean it lower than the critical temperature, which is the horizontal segment here represent possible mixture of a liquid and vapor. So under the dome here, we have the region of vapor and liquid. Okay, ranging from 100% liquid. So maybe we have 100% liquid at left here. Okay, let me. Okay, so this is the dome. So this line here, maybe we have 100% of the liquid. And this is 100% for the vapor. So if we have T higher than TC, that means the temperature is higher than critical temperature. So we can see the region is, the temperature is not cross the boundary at all. And then this condition is called as the superheated region. That means it cannot turn back to the liquid vapor region. So this line here, we call as the saturation line, whether the saturation for the liquid or saturation line for the vapor. It depends on the condition it depends on the molar volume and also the temperature. Okay, I already mentioned about the dome here, so I hope that you can clear that. Okay, this is summarized on the phases based on the PV diagram. So we can see here for the first line, we have the steep line here is based on the solid region. And then we move here to 2, here we have two phases, solid and liquid. If we move next to this line or higher molar volume, that's when we have this liquid region. And this is where we have the, under the dome, we have two phases, liquid and vapor. And then this is for the vapor region. That's mean if we have the temperature higher than the TC, that's mean that phases or the substance cannot be turned back to this vapor liquid anymore. It called as the superheated. And we have this vapor, and under this triple line, we have the solid vapor region. Okay, let's have a break first. Okay, while we having a break, okay, let's ask yourself, why do we learn the PVT diagram? What is important for the PVT diagram? I hope that you can take a break while thinking of the answer for this question. Okay, let's move to the next. We have the single phase region. Okay, at single phase region in PV diagram, there is a relation connection between pressure, vapor, and temperature. Okay, back to what is the PV diagram. So we have PV. If you still remember, we have this, right? The steepest here. Okay, this relation known as PV, and the line here is temperature, right? So we have the relation PV, PVT, PVT properties. We have the relation between that properties. So this relation as known as PVT equation of state or function of pressure, volume, and temperature. Okay, if V is considered as a function of temperature and pressure, then we can write the correlation by using this. We have V equal to V as function of temperature and pressure. Okay, if we turn to the mathematical equation or mathematical modeling, we can have the dV here equal to dou V with respect to the temperature at constant pressure, dt plus dou V with respect to the pressure at constant temperature, dP. So we have two, if you notice from this equation, we have two group here based on the at constant pressure and also at constant temperature. Okay, for the constant pressure, this expression known as the volume expansivity. That means we can equal to the beta. But for the second expression, we have the based on the isothermal compressibility or known as the kappa. And if we combine this equation, we can have another expression dV over dV over V equal to beta delta T minus kappa delta P. Okay, basically this is the expression to simplify the correlation or the relation between PV, T. Okay, because the isotherm on the left of PV diagram are very steep. Okay, what it called as very steep PV here. So we have this line. We have this. Okay, so this is a steep. So both constant are almost equal to 0 because volume has the insignificant effect to this line in this region, right? And this steep line or this region known as the incompressible fluid, where is no equation of state since V is independent of temperature and pressure. But if we still required or needed to calculate for the liquid, so the beta here is positive and K is positive as well. We can calculate based on the difference between the temperature and pressure. Because if you still remember that we have the solid here and we have the solid plus liquid here. So for the liquid, we can calculate it based on the difference between the temperature and also the difference of pressure. Okay, next we move to the equation of state. Since we previously we talked about the TPV, relation, right? So any equation that relates to the TPV of a substance known as the equation of state. So the example, the simplest form of equation of state is the ideal gas law. We know that PV equal to RT. So we have the PV or PV and T, the relation PV and T. So known as the equation of state as well. So the equation of state can be categorized into virial equation, generalized correlation, and QB equation of state. Okay, this is the general definition for the equation of state, which is describe the properties of fluid, mixture of fluid, solid, and its interior. Okay, we move to the first category, which is the virial equation. Okay, if you still remember that for the ideal gas law, we have the PV RT. But the equation of state to discuss about the real gases, so we introduce the compressibility factor or dimensionless ratio to modify the ideal gas equation to the real gas equation, because in a real situation there is no more ideal, the gas is not ideal at all, right? So we can use this virial equation to describe the real gas equation. Okay, there are two forms of virial equation. We have this whether by using this or prime here or B over V. This we have B, C, and D, and so on. Is based on the term, how many terms that we can use. Normally, for the virial equation, it can be up to second term. So that means we can have up to C only. Okay, the other form of virial with as standard for the virial equation, we have the Benedict-Webb-Rubin equation. So these are the another as standard for the virial equation. Okay, back to the ideal gas law. Since the ideal gas law is the simplest form for the EOS, equation of state, let me share to you how that the ideal gas law is established. Okay, if we have pressure at 0, if we plot the pressure versus P, PV versus P at 0 bar, we can have the same value of PV for all the gases. But if we introduce the pressure, if we increase the system or increase the pressure in the system, there are certain or the gases has its own value. So by using this, we can have the correlation where we discuss or describe the process or the condition based on the PV equal or eccentric equal to the A. Okay, we name as A. And then these properties of gases is the basis for the established and absolute temperature scale, because we know that P have this significant or have the effect to the temperature. That's why we have the PVRT. So this is how the ideal gas law is established. In the limit of P to the 10 to the 0, the molecules separate by finite distance because it starts to have the interaction between the molecule. Okay, the volume becomes negligible compared to the total volume of the gas, and the intermolecular forces approach 0. Okay, this condition become an ideal gas state and establishes the ideal gas temperature scale. That's why we have the different of the gas universal based on its units. Okay, this is your assignment. I hope that is not too earlier for me to give the attendance proof. Your task is please provide to me by describing the process. We have the isocurrent, isothermal, adiabatic, based on the internal energy, U, heat, and also what is the difference between each processor. So you may summarize in a table, or if you able to give more an attractive way for me to be evaluated, you may give it to me. So I will publish the, I think the most, I will publish the work in the items for the most attractive attractive summaries to me. Okay, you may submit to me after this. Okay, let's take a look for the example. So we already covered for the first equation of state, which is the Virial equation. Okay, B and C is the dimension, is the constant given. Okay, reported value for the Virial coefficient for isopropanol vapor at 200 degrees Celsius. We have temperature and pressure. So we need to calculate T and also V. Okay, the first for the A, the ideal gas law, we know that PV equal to RT, right? So basically, we can determine the volume based on the RT over P. So what we need to do is you need to insert the value of R, and also we can have the value of T here and also the P. Okay, so maybe you can, I give you the answer and then you can try to insert by your own. Okay, the example 3.7 here, because I am referring to my reference book. So I give you example, the answer for this, we have 34 cm32 over mole. So this is the first answer for A. And then second, using the Virial equation. What is the Virial equation? PV. Okay, back to here. So we have the, so Z equal to, or PV. Okay, so you may use this based on the A and based on the C and B and C. So we have PV equal to RT plus B, right, plus C, etc. So basically, if we have V here, I can write down the equation first for you. So we have P equal to RT V squared and so on. So if we have V here equal to RT over P plus B, right? So we can have, okay, there is no more prime. If we need to use prime, that's mean we can have prime plus C prime. Okay, so we have this, you can use this and then insert the value of R and also T. Okay, you can use this. Since it's based on this, so it turns to cm cube plus, what is the B here? So your B is minus 388 cm3 per mole. So you can get the answer for B here, right? So your answer is 3546 cm3 per mole. And then you may calculate the incompressibility, the compressibility factor here. So Z here equal to PV over RT, right? So you may, if you, so you can V, or you can rearrange here, V equal to RT over P, right? So by using RT over P, we have this, and then it turns to, oh, I hope I can have, okay. So let me get this number 1, and then number 2 here. So you move to here, Z equal to V over RT. So V here, what is our V? You can just play around or rearrange this to RT over P we have. Otherwise, you need to calculate or insert one by one the value. So we have 0 point. So we have done for B. How about this C? I hope that you can, okay, this is A, B, and C here. Okay, for the second order, that means we're gonna use the term of C. Okay, for the C here, since we have V equal to RT P1 plus B over V plus C over Z square. Okay, what is the value that we need to insert to this? Okay, let me explain to you. Okay, so basically we need to perform the iteration for this equation because we don't have the value of V, the exact value of V. So we need to iterate until we found that V at the outside is almost similar to V in the inside. So let's start with example. We have V1 here. So this is turned to V naught, right? So to obtain the value of V1 here, what we need to do is we need to assume the V naught here. So you may start with this value. So we have the V1 here equal to RT over P. We have this one. So I just insert this value. So RT over P, you may use this. And then we can have 1 plus B, you can insert this 388 over V naught here, we may use 3. And then plus C here, minus over V naught, okay, square. And then you may find if this value, if V here, V1 here is near or not with this. If not, you need to perform another iteration. Another iteration, that's mean V1. Okay, we have another iteration. So that's mean 3. So 1 minus B over V1. So the V1, the value of V1 here, you may insert to this. Okay, I hope that you are clear. So you may try by your own. So the answer is after a 5 iteration that I did, we have V equal to, not V1, but V. So after 5 iteration, equal to mole. So you can find the value of Z. So insert the value 3 point. I hope that you understand. You may try by your own later, okay? So 39. And then the answer is 0.8899. Okay, so this is how we solve this, calculated the molar volume and also the Z based on the comparing the ideal gas and also the Virial equation. Okay, we move to the next category, which is the QB equation or state. Okay, the QB equation can represent both liquid and vapor properties. Okay, before I proceed, okay, the QB or state can be categorized or can be classified into, we have the van der Waals, we have Redlich equation, we have this SRK, so Redlich, Kwong equation, and Bang-Robinson. Why we have the different type of the equation under the cubic equation of state? Okay, we should know that this equation is not perfect. All the equation is not perfect. Okay, example for the Redlich, for the van der Waals. Okay, the van der Waals equation is applicable at low temperature and pressure. So that's mean the scientists come up with a new equation known as Radwicz-Kohn, okay, after their name, to proceed with. That means they introduce another equation to overcome with the limitation of the van der Waals equation. Same goes to the SRK and Bang-Robinson. Okay, basically the cubic equation of state is the polynomial equation that is described based on the volume of the properties of the system. Okay, let me share the explain more. Let me open the whiteboard. Okay, based on the PV, based on the PV diagram, okay, we have here PV. So for the PV, we have the here, and then we have the under the dome, right? And then we have the temperature example. So this is how we have this. Okay, back to here. Okay, to study the effect of volume. So under the dome, we're gonna have the example here. We have this. So this is the volume, saturation volume for the liquid, right? And then this is the saturation volume for vapor. And this is maybe our condition V. And then we have another. Okay, this is our first. But the second, I give you another example. If we increase more the temperature, so we're gonna have a new volume or saturation value for liquid, and then we're gonna have another saturation volume for vapor. Okay, based on that, if you can see that we have the different. For the first temperature, maybe T1. For the T2, we have another saturation volume for both liquid and vapor. Okay, based on that, we can see that the significant volume into the system, right? So that's why we come up with the cubic equation of state that explain the effect on the volume into the system. Okay, these are the general equation for the cubic equation of state. We have pressure equal to RT volume minus B. Okay, B and A is the constant. So B here accounts for the space molecule occupied. So in the system, we consider the space of molecule occupied. And A here accounts for the attractive interaction between molecule. So if you notice that this cubic equation of state also modify the ideal gas that mimics to the real gas properties. And these are the epsilon here, and also we have the here will be explained or will be described based on the equation of state that I mentioned previously. We have the van der Waals, and we have this. We have van der Waals, we have a Rishkin, and then we have SRK, Pan Robinson. So the value here is differ. or the constant here is differ for each equation. So I think that is more clearer if we can take a look for the example later. So let's move to the generalized equation. This is the last equation of state. Okay, the generalized equation is based on the modification by using the compressibility factor. Okay, for the Virial equation state, we depend on the compressibility, but for the generalized equation, which basically apply at higher pressure, we're gonna introduce Z naught and also the eccentric factor and as well as Z1. Okay, Z naught and Z1 here may be obtained from the table 1 to 4 in appendix A, and it can be defined by calculate the reduced temperature and reduced pressure, because the different TR and also PR can give the different value of Z naught and Z1. Okay, the eccentric factor is different for each substance or gases. So you may refer this value to the table B1 in appendix B. Example for the methane, hexane. So methane, we have maybe ethanol, we have the different of the eccentric factor. Okay, for the gas here, you can use this information, how to define the Z0, Z1, or otherwise you can refer to the appendix. And for the liquid, we may use the Racket equation. Okay, for the V or the critical volume, you may determine by using the based on the density, right? So we can have the volume here. So for the ZC as well, you can based on the Z equal to PV over RT. So you may find the ZC here. Okay, so we can take a look on the equation that for you to be more clear, more understanding about this. Okay, what pressure? So you need to define the pressure is generated when one or pound mole of methane is stored in the volume. We have P here, and we have the temperature. Base calculation on each the following. So what we need to do is to extract the information first. So change the color. Okay, so the volume is given 2 feet, the cube, and then we have the temperature 1, 2. Okay, so in order for us to calculate the pressure, we need to select or choose the value of universal gas constant. Okay, back to the previous slide. If you notice that there is no Fahrenheit unit, we have only Kelvin and also the Rankine. So basically we're gonna choose the Rankine. So because it based on the feet, right? So we're gonna change the unit from the Fahrenheit to the Rankine here. So for the temperature, what we need to do is we need to plus the 409.67 to convert it to the Rankine. So this is, you may calculate R. Okay, and then after that, what is the information? So you need to find the value of R. So the value of R is 2. So the unit is, okay, so the unit is feet cubic, ATM, pound, mole, and also we have the Rankine. So that's why we convert the temperature from Fahrenheit to the Rankine, because we need to cancel the unit by using this value of the gas universal. Okay, so we start with A. PV equal to RT, because for the ideal gas there is no compressibility factor. factor introduced into the equation. So to determine the P here, RT over P. So R here 0.7302. Temperature we have. And also V here is 2. So we can get the answer here is, okay, let me share to you. The answer is 212.4 atm. Okay, for the B, RK equation, what is Redlich-Kwong equation? So P equal to RT V minus B A B V plus B. So we need to R is we have the value of R, T as well, V as well. So we need to find the A and B. So A here equal to, okay, you need to refer back to this table. So for the Redlich-Kwong we have, so A here, okay, this is the general equation. So we need to use this equation, alpha TR R squared PC squared PC. So we need to find your pressure, critical pressure, and also the critical temperature. So first, we need to define A. So we need to define the TC and PC first. How can we define the PC and TC? So you need to refer to your appendix B1. So for in appendix B1, TC is for methane. So refer to the methane. TC is 3143.1, and for A here, A equal to 0.427. So I just use the equation. You may check it later, okay? So you can try by your own. You can try by your own later. So I just insert, okay, for RK here, we may have this value. And then use this equation. You need to insert the alpha here. Alpha is TR power of minus 1/2. So the power TR here, TR, T over TC. So we're gonna have T here over 3431. So it gives the value of 1.9695. So TR here we have 1.9, okay, minus 1,2, and then we have R here 0.7302 square, and we have the TC, so 343.1. Okay, you may refer it back later, okay? So I just give the solution, and then we have, okay, this is our, okay, this is our A here, so we need to PC. So you can refer to the appendix, and this is your PC. So PC is given from the appendix, okay? PC is 0.44 methane. And then we can have the A here is 453.94 atm feet power of 6. And how about B? B here, the constant for B here. So B here is, you may refer to this one. I still need to go back here. So you can refer this is the general equation to find the B, and then B here for RK, you may use this value. Okay. So B here is 0.08664. We have R here 0.7302, and then the TC 343.1, and then to BC. So we can get the B here is 0.4781 feet cube. So P here, since we already have all the information, just insert the values. P here, so 2 minus B is 0.81. I hope that you understand how can I get this. Okay, you may try by your own. Those you can understand how to solve this. And then the answer is 187.8 atm. So this is the first for A ideal gas. So you can see the differ between the pressure by using the equation, the different equation. So for the C is generalized. Okay, basically the generalized equation is based on the Lee-Kessler. Okay, this equation can be used at higher pressure. Normally is more accurate at higher pressure. So if you notice that the pressure is quite high, right? So basically, if the problem is given to you, you may automatically use the Lee-Kessler or generalized equation. Okay, for the generalized equation, we have P Z R T over V, right? So this is the, if you still remember that for generalized equation, we use the equation based on the compressibility factor. So we need to find the Z, right? So based on that, we can determine the P by using this equation. P equal to ZRT over V. So you need to determine the Z first. How can you determine the Z? So I don't have the value of Z0 and Z1 because we don't have the value here. So we need to create the correlation. So based on this, we have P here, Z, we don't have the information on Z. So we have 0703, and temperature also given to us. And V is 2. So we can have 212.4 Z, right? So P equal to 212.4 Z. And then after that, you can have the Z equal to 212.4 over P over P. Or P here, if you have a P R equal to P over PC. So P equal to PC PR. So basically we need to find the correlation. So we can have this 2124 over so we have this correlation. Okay, and then what we need to do is, so we can have the or P here, Z here, okay. So we have the, okay, P here, PR, we have the PC for 24. Okay, this is the PC, okay. Okay, PC already defined, right? Because we have the methane, so ER. So you may insert to this. So we have Z equal to, because Z we know that we have the PR to this. So we can have this P here 212.4 over, okay. So we have the, actually this correlation is, we need to have this kind of the correlation because we need to, we don't have the value uh, of the Z, yeah. So we need to have this kind of the correlation. What is the, how can we correlate it? So by using this, so we have Z equal to, so we can start this. Okay, how about if we have Z equal to 1? So that's mean we have the, if Z equal to 1, we can have the PR equal to 4.68, right? By using this 4.68, we can refer to the appendix to define your Z known as Z1. Okay, at appendix E4 and E5. And E5, because we need to define the Z node and Z1. That's why we need to have this correlation, or try to have our first assumption. So at PR here and TR is at 1 point. Okay, this is the TR, because T already given but not the P. That's why we need to find the PR, because we know that PR is based on P over PC, right? PC, we can get the PC, but we don't have the value of P. That's why we need to find the PR. So PR is based on the assumption that we start with Z equal to 1. So by using PR and TR, this value of PR and TR, so we can have the value of Z node from the appendix is 0.887 and Z1 equal to 0.258. So you can find the Z is 0.887 plus eccentric factor is a fixed value, because we may refer to the appendix B1 for the methane. So I hope that you understand about this. So you can have the value of Z is, okay, what we need to do is we need to start, okay, since we start with if, right? So it is uncertainty for us. So we need to proceed with Z equal to 0.890. So we can get the new PR. So, and then you can get the new PR by using the same TR here, because T is given. And then you need to ensure that the Z here is the calculated Z is equal to the given Z here. So after a few iterations, we found that the Z here is equal to, after a few iterations, I found that Z here is the equal to 0 point. I mean, this is the equation that we choose is the Z is equal to 0 point. So you need to, okay, find the Z is 0 point. Okay, this is why what we have here. I think that this is almost similar, because 0.89 and 0.997 is almost similar, right? So Z here is 0.890. So P equal to ZRT over V. So we can get P here is Z 0. I hope that you understand about this. So T here over 2. So you can get P here is 18. Okay, we can have this P, so the value is different. So basically, we can say that the most accurate, okay, we have is at by using the generalized equation. Since P is higher, so you may use after this if the problem is given to you. So please take a look on the value of P. If P is higher, you may choose the generalized equation or Lee-Kessler equation to proceed with. Okay, in summarize, we can conclude that for the ideal gas law is applicable at lower pressure with below than 2 atm and temperature at higher than 25 degrees Celsius. And this by using this correlation for the PR and also the TR. So for the van der Waals equation can be used for the vapor only at low pressure. For the virial equation, same with the van der Waals, but we may have the correlation for the TR and PR. Rayleigh-Korn equation also can be used at lower pressure and at the vapor only. And for the SRK, it can be used for the saturated liquid and vapor and high pressure. And for the Bank-Robinson, it can be applied to the in hydrocarbon industry standard. Okay, in overall, by differentiate between the gas and liquid. For the gas, we can use the ideal gas law and second term Virial equation as well as the QB equation of state. But for the generalized, you may use the Lee-Kessler table by refer to the appendix E to define your Z0 and Z1. Okay, for the liquid, we already learned about the incompressible liquid that relate to the beta and also the kappa. And we can use the Rakat equation that we need to define the critical volume and the critical Z here. And then I already mentioned about this constant beta and also kappa based on the volume of expansivity and isothermal compressibility. And then last is the generalized equation using the Rakat equation. So in summary, we can conclude that we already covered the PVT diagram. You already know about the correlation between that properties. We already described the ideal gas equation and the real equation based on the equation of state, right? As said that ideal gas law, we have the other equation that can explain the ideal gas equation of state to refer the real gas. And then we already know how to apply the ideal gas equation of state in the solution of typical problem. And last, we already introduced the Z factor for the virial equation and generalized equation. And we already present some best known of equation of state based on the its application. I hope that we already cover all. Maybe you can try by your own to all the example given to you that to ensure that you are more understand about that. Okay, for the next topic, we will move to the next chapter, thermodynamic properties of fluid, which we will learn about the thermodynamic network through Maxwell equation. And we're gonna learn in detail about two-phase system, vapor liquid, and also the residual properties. What is defined by the residual property? Okay, before I end my lecture, I hope that you can submit your attendance proof to describe the internal energy, the work, and also the heat for the different type of the process, such as isothermal, isobaric, isochoric, and also the adiabatic. So you may summarize it in a table or depend on your creativity. Okay, by that I end our class today. Thank you for your attention and have a nice day. Bye.